All right, everybody. This chapter we want to study the issue of heat and heat transfer. Um, Now, heat itself, okay, is a form of energy, so it's going to have the units of joules. Um, and there's a story about how heat was discovered to be energy, and this is the story that's told at the beginning of your chapter. And it was discovered that if I have a um, vat of water, right, and inside the water I have a paddle wheel, and I'm going to seal the water off, and I have some sort of crank that I can spin the paddle wheel with. If I can spin the paddle with enough speed, um, then the temperature in the water is going to rise. And we see that by putting a thermometer in here. And this experiment was first done um, with some fairly, by modern day standards, primitive technology, but it's what they had to work with, and it was demonstrable. So even with the equipment they had, um, I can't remember. I believe the thermometer was probably a mercury thermometer, and because they could fashion glass and so forth fairly accurately and precisely, even a couple hundred years ago, they were actually able to measure this, and this is what initially gave the determination that heat and energy, or heat was a form of energy, right? Heat and energy, heat and energy are not exactly the same thing because not all energy involves heat, but heat is a form of energy. And when two substances come into contact with each other, okay, they're going to exchange heat if they are at different temperatures. Now, what is temperature? From a physicist point of view, that's actually a little fuzzy to define. Um, but for our purposes, we'll just call these two objects A and B, and we'll call this temperature 1, and we'll call this temperature 2. And as long as these two objects are in contact with each other, and thermal contact for our purposes simply means that they're close enough to each other that they will exchange heat. So if T1 does not equal T2, then the objects will exchange heat. Okay? If the temperatures are not equal, then heat will be exchanged. Now, heat flows from hot to cold. Okay? Heat flows from hot to cold. And this is true in every situation we're aware of. This is actually based on the second law of thermodynamics, which we will talk about, but not in this video. But when we get to it, I'll come back and mention this, okay? This is due to the second law of thermodynamics. There's no physical reason, okay, in any given molecular exchange of energy. Um, when you look at things at the atomic level, there's no reason why when two molecules exchange thermal energy, you can't get a situation where one individual atom um, exchanges energy in the form of energy flowing from a colder object to a hotter object. You can have that. The situation with this, however, is when you start to look at systems macroscopically, um, the probabilities are simply overwhelming that the heat will flow from hot to cold. And by overwhelming, we mean to take that as even for a small system, okay? Such as, for example, a cup of hot coffee um, being set in a small container of lower temperature air. Um, the probabilities that the coffee will actually get hotter um, and the air around it get cooler and heat flow from the cooler object to the hotter object, the probabilities of that happening are so vanishingly small that we would not expect to see that in the known history of the universe, which is roughly 14 billion years. So, for all intents and practical purposes, we say that heat flows from hot to cold, and this is a general law that flows from the second law of thermodynamics. But in any case, okay, um, one of the things that your book starts to mention right away is this issue of heat exchange, right? And we denote heat by the capital letter Q. Okay, so before these two objects, before A and B are brought into contact with each other, we can say that object A has some heat QA, object B has some heat QB. Okay, um, at these two temperatures. Now, the amount of energy that's exchanged between these two objects, okay, the amount of energy that's exchanged between these two objects, I'm going to call heat 1 and heat 2. Okay, I'm going to call heat 1 and heat 2. So QA is the amount of heat that object 1 has, or object A has initially. QB is the amount of heat that object B has initially. But heat 1 is going to be the heat exchanged by object 1. So this is going to be some of the amount of heat that object 1 exchanges. Now we're going to call Q2 the heat exchanged by B. Okay? So here is the rule. All right? If we put these objects in an isolated system, in other words, I put them in a box, and that box is a thermally insulated container, and heat from the air is not flowing in or out of the box, and therefore only we can even go one step further and claim that the box is a vacuum. um, so it's a perfect insulator, and under that condition where A and B are only in thermal contact with each other and nothing else, okay, when A and B are in thermal contact with each other and nothing else, then the heats exchanged by A and B must add up to 0. So these two objects are at different temperatures. T1 and T2 are not the same. For our sakes, let's just assume that T1 is larger, or larger. Let's just say that T1 is larger than T2. Okay? So what this means is if T1 is larger than T2, then heat is going to flow from object 1 to object 2, or from object A to object B. And under that circumstance, then the amount of heat that is exchanged by object 1 is going to, let me put it this way, the amount of heat exchanged by object 1 plus the amount of heat exchanged by object 2 has to add up to 0 when I look at the system as a whole. Okay? So no energy is being lost by the system, but some dynamical things are happening within the system. So what this means is that one of these heats must now be negative. Okay, one of these heats must now be negative. One of the heats is going to be losing temperature. One of the objects is going to be losing temperature. The other object is going to be gaining temperature. Okay, so what we can say now is that Q2 is going to be equal to negative Q1. Okay, Q2 is going to be equal to negative Q1. Now, what are the forms of these heats? Okay, what are the forms of these heats? Well, what is heat proportional to? You can imagine that heat should be proportional to mass. The more of object A I have at a specific temperature, the more heat it's going to have to move. The more heat it's going to have available to move. So Q is proportional to mass. And Q, the amount of heat to be exchanged, is going to also be proportional to the temperature differences. Okay? Q is going to be proportional to the temperature differences. If T1, if the temperature of object A is much larger than T2, then I'm going to have a lot more ability for heat to be exchanged in one preferred direction over the other. Once these two come into thermal equilibrium, once objects are in thermal equilibrium, what that means is that thermal energy is just as likely to be exchanged in either direction. Okay? So once they reach the same temperature, the thermal energy will just simply be exchanged equally between the two objects, and there's no net change for either object, right? It'll gain just as much as it loses. So to have legitimate heat flow, I have to have a change in temperature. There's also something else that heat is proportional to, and this is what we call the specific heat. In other words, your specific heat, okay, we denote by the letter C. Your specific heat is the amount of heat necessary to raise a unit of mass by 1 degree in temperature. Okay? And our specific heats are going to be measured in per degree Celsius. Okay? So if these are two different substances, and one object may be like a metal, okay, metals are typically good conductors of heat, and therefore they heat up relatively easily compared to some substances like, say, water. Water, it takes a lot more energy to raise the temperature of 1 unit mass by a degree Celsius than it does 1 unit mass, equal mass, of something like copper or nickel or iron. And so your specific heat, the lower your specific heat, the more easily heat is going to flow, right? The lower your specific heat, the more heat is going to be able to flow. And so the heat flow for a generic object is equal to the product of these three things. Okay? Is equal to these three things. And remember that delta T, okay? Delta T means final minus initial. Okay? So this delta T that's going to appear on both sides of this equation, I'm going to have a delta T here and a delta T here. Both of these two objects start out at different temperatures, T1 and T2, and they're eventually going to come to an equilibrium temperature once the system has stabilized of TF. Okay? So the amount of heat lost by object 1 is going to be equal to negative the mass of object 1 times its specific heat times the final equilibrium temperature of the system minus its initial temperature. And that amount of heat lost must be the amount of heat gained by the second substance, which is going to be M1, or M2 rather, C2 times, I'll write it out like I did on the other side. TF minus T2I. Okay? So, in this particular example, right, the classical problem here is to solve for TF, right? The classical problem here is to solve this equation for TF. I want to know what the final temperature is if I know the initial masses, the specific heats, and the initial temperatures of both objects, right? So let's do an example. Let's suppose that I have a 2 kilogram block of iron. Let's do copper. Right? And let's say this copper is initially, I'll call this object 1, by the way. The initial temperature of the copper is 100 degrees Celsius. And I'm going to stick this in a bucket of 1 kilogram of water whose initial temperature is right at freezing, but it's still liquid. Okay, and once I dip the copper in, I'm going to seal it off so that no heat is lost to the atmosphere. Okay, so we're going to assume this is a perfectly thermally insulating container. And I want to know what the final temperature of the copper-water combination is once these two come to equilibrium, right? So because I'm dipping the copper in the cooler water, I know that the copper's temperature is going to go down. So the copper is going to be the object that loses heat, and water is going to be the object that gains heat, right? So the temperature of the copper is going to go down, the temperature of the water is going to go up, right? So that means that delta T for water is going to be positive, and delta T for the copper is going to be negative, right? So what we can say is that Q2 must equal Q1. So I'm going to set up this equation. The mass of the water times the specific heat of the water times the final temperature of the system minus the initial temperature of water must be equal to the mass of the copper times the specific heat of the copper times, there's a negative sign here because we're losing. Make that a little bit more prevalent. This should be T2. And that's T1. And so what are the specific heats? Well, there's a table in your text, right? And from the table in your text, you can see that the specific heat of water is 4,186 joules per kilogram per degree Celsius. So to raise, what this means is, assume I have 1 kilogram of water, which I do in this particular case, and I want to raise that water by 1 degree Celsius. if I have 1 kilogram of water and I want to raise it by 1 degree Celsius, it takes 4,186 joules. Okay, that's the interpretation of that number. And the specific heat of the copper turns out to be 387 joules per kilogram per degree Celsius. Okay. Now, another thing to note is that T2I is 0, so I can get rid of that. And I'm just left to solve for TF. Okay. So I'm going to have MWCWTF is going to be equal to MCCC, and the negative sign distributed means that this is negative and this is positive, so I'm going to say something like this. So since I'm solving for TF, I want to group those together on the same side. And something else I can do, since the masses are just off by a factor of 1, right, I can insert 1 for the mass of water, and 2 for the mass of copper. And I'm going to drop the units because kilograms on both sides will cancel out, and I'll just be left with their overall factors. And so I have something that looks like this, right? I have something that looks like this. And so this is just going to be, I'm going to factor out the TF, and this is going to be CW plus CC TF is going to be equal to twice CC TI T1I. And so now in our particular example, the final temperature is going to be twice the specific heat of the copper times the copper's initial temperature divided by the sum of the specific heats of, so that needs to be a 2. Plus 2. So CW plus 2CC. So this is going to be 2 times 387 times 100. And this is going to be divided by 4,186 plus 2 times 387. And this is in Celsius. This is in the units of joules per kilogram per degree Celsius. Both of these are in joules per kilogram per degree Celsius, so those cancel out, and I'll be left with just with Celsius. And you do the calculation, and you get, if I did the math correctly, if I did the arithmetic, you should get 15.6 degrees Celsius. So the final temperature of the water copper system will be 15.6 degrees Celsius. Okay. All right, so we'll pause there for this video, and in the next one we will talk about latent heats of vaporization and fusion, as well as heat flow with conduction, convection, and radiation. All right, we'll see you in the next one.